In this video lecture, you will learn how to check that the solutions of the ordinary differential equations, the mathematical model that you have derived of a physical system, have the two fundamental properties, existence and uniqueness. These two properties are essential for the ordinary differential equations to be a useful mathematical model of the physical system. After watching this lecture, you should be able to validate the mathematical model by ensuring the existence and uniqueness of the solution of an initial value problem. The video lecture is based on section 3.1 in the book Nonlinear Systems by Khalil. We are given a physical system that we want to control. We create a mathematical model of the system, which we will use for analysis and control design. And the model consists of a set of ordinary differential equations, which in vector form are written like this. In order to be an appropriate mathematical model of the physical system, it needs to have certain properties. For a physical system, we expect that starting an experiment from a certain initial state at time t0, the system will move and its state will be well defined in at least the immediate future time. In addition, for a deterministic system, we expect that if we repeat the experiment exactly with exactly the same initial state at time t0, then we would get exactly the same motion. For the ordinary differential equation to be an appropriate mathematical model of the physical system, we thus expect the same. There should exist a solution to this initial value problem here, and this solution should be unique. So how do we find out if this is the case? How do we validate the model by checking that there exists a unique solution to the initial value problem? We have some sufficient conditions that we can use. Theorem 3.1 states that if the vector function f is piecewise continuous in time t, and f satisfies the Lipschitz condition in the state x, then there exists a unique solution to the initial value problem locally. Piecewise continuous in time. This means that the function should be continuous in all except from a finite number of points in the time interval of question, which is from the initial time t0 to some time t1. The time t1 can be infinity, but it does not have to be that large for this theorem to hold. The Lipschitz condition is a stronger condition than continuity. The Lipschitz condition is the requirement that if you evaluate f first in x and then in y, and you take the difference between these, then the magnitude of this difference, the norm of the difference, should be less than or equal to some constant L times the magnitude of the difference between x and y. You can use any p-norm to check the Lipschitz condition. Choose that which you find the simplest to use. Theorem 3.1 gives sufficient conditions for local existence and uniqueness of the solution of the initial value problem. Specifically, the solution is only guaranteed to be well defined in the immediate future up to some time interval delta after the initial time. Note that L has to be a positive constant. That it has to be positive follows naturally from the properties of norms, so the important thing to notice is that it has to be constant. It may not vary with the time t or the state x. To illustrate this, we can check this condition for the simple linear scalar function f of x equals a scalar a times x. We first find the difference between f evaluated in x and f evaluated in y, and then we take the norm of this. So f evaluated in x is ax, and f evaluated in y is ay, and we have the difference and we take the norm of this. And we want to relate this to the norm of x minus y. By the properties of the norm that we talked about previously, we can move the scalar out, and this is thus equal to a times the norm of x minus y. So the scalar linear system satisfies the Lipschitz condition with an equality and with the Lipschitz constant L equals the scalar A. Let's then look at a general scalar system where f maps a real number to a real number. So this system is scalar and not time varying, but it is no longer a linear system. What does the Lipschitz condition look like then? In this case, the norm can be replaced by the absolute value, and the Lipschitz condition says, if we rearrange it a little, that the absolute value of f of x minus f of y divided by the absolute value of x minus y should be less than or equal to some constant L. And what do we have on the left-hand side here? This is the slope of a straight line joining any 2 points of the function f. So the Lipschitz condition in this case says that this slope cannot be infinitely large, it has to be bounded. So in other words, the Lipschitz condition says that the function should not grow too fast. Take for instance this ordinary differential equation, dot x equals the cube root of x. The system starts up at the zero state at time 0. Does there exist a unique solution for this initial value problem? Pause the video and see if you can use theorem 3.1 to check this. We need to check whether the conditions of theorem 3.1 are satisfied. The system is time invariant and f of x is the cube root of x. The first condition of being piecewise continuous in time is thus trivially satisfied, and we only need to check the Lipschitz condition. We already saw that for scalar time invariant systems this could be rewritten as the absolute value of the slope of a straight line joining 2 points x and y of the function f having to be bounded. Therefore, any function that has an infinite slope at some point does not satisfy the Lipschitz condition of theorem 3.1. The function here looks something like this. And we see that the slope around 0 does not seem to be bounded. We can check this by looking at the magnitude of the derivative of f with respect to x. This is the absolute value of 1/3 of 1 over x raised to 2/3. And it is clear that when x goes to 0, then this goes to infinity. So the function has an infinite slope at 0, and therefore it does not satisfy the Lipschitz condition of theorem 3.1. Consequently, theorem 3.1 does not guarantee that there exists a unique solution of this initial value problem. This initial value problem is actually possible to solve analytically, and doing so we can prove that there exists a solution, but it is not unique. Actually, both x of time t equals 2/3 times t raised to 1.5 or 3/2 is one solution of the system, and x of t being identically 0 is another solution of the initial value problem. As we have seen, the key assumption in theorem 3.1 is the Lipschitz condition. If a function satisfies the Lipschitz condition as it is stated in this theorem, we say that the function is locally Lipschitz. And sometimes we specify that it is locally Lipschitz at the point x0. Furthermore, a function is said to be locally Lipschitz not only at a point, but in a domain D, if the function is locally Lipschitz at any point in this domain. Note that the Lipschitz constant L can then be different for each point, so L can vary over D. If the Lipschitz constant is the same for all the points in D, then the function is said to be Lipschitz on the domain D. So note the difference here. Lipschitz is a stronger property than locally Lipschitz, because the Lipschitz condition must be satisfied with the same Lipschitz constant L at any point in D. And if a function is Lipschitz on the whole state space Rn, then we say that it is globally Lipschitz. In other words, the Lipschitz condition has to be satisfied with the same L, the same Lipschitz constant, at any point in the state space. You can read more about this at page 89 in Khalil, and I also recommend that you go through example 3.1. And for those of you who wondered what a domain is, a domain is an open and connected set. So we have some set D. That it is open has a very precise mathematical definition. But you can interpret an open set as a set that does not contain its border. That it is connected means that any two of its points can be joined by a broken line of finitely many straight line segments that all belong to the set D. So you can take any 2 points, one point x here and one point y here, and you can connect them by straight line segments and finite number of them without leaving the set. In other words, the set is only made up of one piece. We have seen that for time-invariant scalar systems, the Lipschitz condition is related to the slope of the function. This observation can be generalized to time-varying vector-valued functions, and this is done in Lemma 3.1. Consider a vector-valued function f that maps the time in an interval from a to b and the state in a domain D to an n-dimensional vector. If the function is continuous on this time interval and the domain D, meaning that it is continuous in time on this interval from a to b, and continuous in state on the domain D, and if the first order derivative with respect to x exists and it is continuous on a to b and D, then the first condition of Lemma 3.1 is satisfied. The second condition states that there should exist a convex set W in D, and there should exist a constant L such that the norm of the first order derivative with respect to x is bounded by this L for all time in the time interval from a to b and for all states in the convex set W. Note that it should be the same L for all values of time and state. So it should be possible to find an L such that this is satisfied for all x in W and for all time instants in a to b. Another way to state this is to say that the partial derivative of f with respect to x is uniformly bounded on a to b and W. If these conditions are satisfied, then Lemma 3.1 says that f is Lipschitz on the set W. The lemma thus shows how a Lipschitz constant L can be calculated using knowledge of the partial derivative of f with respect to x. So we can use this lemma to find a Lipschitz constant L, and then, having showed that f is Lipschitz on W, we can evoke theorem 3.1 and conclude about existence and uniqueness. We use the term convex. A set W is convex if lambda times x plus 1 minus lambda times y is in the set W, where lambda varies between 0 and 1, and this should hold for all x and y's in the set W. So given a set W, this is convex if for any 2 points x and y in the set, we can draw a line segment between these points. Such a line segment is described by lambda x plus 1 minus lambda times y, where lambda varies between 0 and 1. If lambda is 0, then we get y, and if lambda is 1, then we get x. And for all other values of lambda, between 0 and 1, we get the points on this line segment. The set is convex if this is satisfied. In particular, the set is convex if the line segment is contained in W. And this should hold for all x and y's in W. So the set is convex if the line segment between any 2 points in W is contained in W. This set, for instance, is not convex because we see that the line segment connecting these 2 points is not contained in the set, but it leaves it. So Lemma 3.1 gave a condition for the function being Lipschitz. The first condition of this lemma was that the function should be continuously differentiable. What if this is the only condition that is satisfied? What if the function is continuously differentiable on the set A to B and D, meaning that the function is continuous on the set and that the first order derivative exists and is continuous on the set? Without the second condition of Lemma 3.1, which required that the partial derivative should be uniformly bounded, we can no longer conclude that the function is Lipschitz on the set, but we can conclude that the function is locally Lipschitz on the set D. And locally Lipschitz is all that is required in Theorem 3.1, which concerns local existence and uniqueness. You can read by yourself Lemma 3.3, which is a straightforward extension of Lemma 3.1 and which gives sufficient conditions for the function to be globally Lipschitz, and Theorem 3.2, which gives sufficient conditions for global existence and uniqueness. I also recommend you to go through example 3.2, which illustrates how you can use the definition of Lipschitz in Theorem 3.1, and that the lemmas only give sufficient, not necessary conditions for the function being Lipschitz. One interesting thing to note from Lemma 3.2 is that the function being continuously differentiable implies that it is locally Lipschitz. It can be easily shown that the local Lipschitz property of a function is stronger than continuity, and therefore this again implies that the function is continuous. So the local Lipschitz property lies between continuity and differentiable continuity. It is easy to think that if a function is continuous, then it's also locally Lipschitz, but the example that we considered earlier demonstrates that this is not true. The cube root is continuous, but it's not locally Lipschitz. So continuity is not sufficient, but differentiable continuity is.